Okay, so what you need to know about the national grid in the UK. So this diagram gives a pretty good layout. So you have various methods of power generation. In your previous work, you've done things like wind turbines, wave power, hydroelectric, fossil fuel power stations, nuclear power, etc. So method of energy production. From there, it goes through something called a step-up transformer. From the step-up transformer, it goes through a series of overground and, as it happens, also underground high voltage transmission lines. That gets it from where it's being produced to where it's being used. Then you have a step-down transformer, and then that brings it into the home for the consumer to use. So you need to have an idea of some of the values that are involved along this process. So it varies along different parts of the national grid, but the actual cables above and below ground can carry anywhere up to 400,000 volts in the cables running through the system. Or if you prefer, you could put that as 400 kilovolts. Now, as you can see, that's a very, very high voltage or potential difference. It's down to 11,000 at the step-down transformer. And there's a reason why it drops from the 400,000 to the 11,000 by the time it reaches the transformers along some parts of the system. And then that changes it down and it turns it into 230 volts for a domestic user. So there's a few key things that you have to know about the national grid. First of all, it is a 230 volt RMS supply. We go into this in much more detail in a later topic. What that means is, rather than having just 230 volts as if you had a 230 volt battery, so if you had a graph of potential difference against time, that would be a 230 volt battery. That's not what happens. What you actually get is a constantly changing potential difference, which swaps direction several times. So it constantly changes. So one moment it's a potential difference pushing one way, one moment it's a potential difference pushing the other way, and this goes to slightly higher than 230. So that's so 230 is maybe just a little bit below there, and slightly lower, if you like, than minus 230. But what this does, this delivers the same average power as if you had a 230 volt battery. You go into more detail on that another time, but that's kind of the crux of it. So it's a 230 volt RMS supply. The RMS just means that basically it gives or provides the same power as a 230 volt direct current supply. So direct current is what you get from a battery. This is constantly changing, and therefore because of that it's called an alternating current, which we call an AC supply. So you need to know that it's 230 volts AC. You also need to know why they bother with the step-up and step-down transformers, what they actually do, and why they have these ridiculously high potential differences of voltages along the way, and then they bring them down to a safer working voltage for use in the home. So when we do the magnetism topic, we do transformers in a lot more detail, but for the moment, what you have to have in your heads is this. Electrical current, when it flows, causes a heating effect. And obviously, that heating effect, in effect, is waste energy. So for all the power you're providing at the start, If there's a heating effect along these miles and miles and miles of cable, then there's an awful lot of energy wasted and not reaching the home at the end. So obviously that's wildly inefficient. However, you can reduce the heating effect by having less current. So less current means you have less heating effect. So if you can get the current much, much lower, then you can reduce the amount of heating effect, reduce the waste energy, and you can deliver the power more efficiently. However, from our equation, P equals IV, if you want to try and deliver the same amount of power, but you are using or want to use a much, much smaller current, the only way to do that is to use a much, much higher voltage or potential difference. So in effect, if you want to deliver the same amount of power at a lower current, you need to provide that at a much higher potential difference in order to have the same amount of power transferred. This also links because a version of the P equals I squared R equation is where this equation actually becomes linked to the power loss and the heating effect. And as you can see, because the current is squared, if you have a larger current, because it's squared, you end up with a larger current squared gives you a larger power loss or heating effect. Whereas if you reduce the current, reducing this because it's squared means it has a bigger reducing effect on there. So this is a little kind of extra thing where, because of this I squared R link, you can't change the resistance of the cables. They are the cables you've got and the length they are. So if you can reduce the current running through those cables, you have less power loss, less heating effect. So that also shows the link. So that just shows that lower current gives you less power loss. They are much more accepting of this explanation and the heating effect here. You don't have to prove it with this equation at GCSE. So the key thing to remember is current causes a heating effect, that wastes energy. If you can reduce the current, you reduce the heating effect. But obviously if you just reduce the current, that would reduce the power, so that's no good. So if you reduce the current, you have to increase the potential difference or the voltage to get the same power delivered. So going back to the diagram, the energy is produced, the electricity is produced by various methods. It goes into a step-up transformer. That changes whatever you're putting in into a really, really high potential difference, but therefore a very low current. So there you're delivering the same power, high potential difference, but low current, less heating effect, less energy lost. Then eventually you reach a step-down transformer. That turns it back into a safer, more sensible working PD. Also brings the current back up again, and therefore it can then be used in houses, factories, etc. Other things that are worth noting about the national grid. So you can't really store electricity in the national grid system. There's not like sort of big battery banks all over the place, although they are developing ideas along those ways. So what that means is they have to pretty much produce electricity to meet demand. And so there's an ongoing sort of battle where they're trying to constantly balance what's being needed and what they're producing. Power stations, you can't just switch on and off easily. You can sort of turn them down slightly or turn them up slightly, reduce the amounts. Other things like wind turbines depend on the wind at the time. And there's various other things that they have to balance to keep sort of the amount of production to match the amount of need. There's something they can do where they use something called pump storage, where they use spare electricity that they're not using because they're producing more than is needed to pump water from a low reservoir lake into a really high one behind a wall or a dam. And then what that means is that electricity has not gone to waste. That water is now at a higher place. If they suddenly need extra electricity very quickly, they can open the valves in the dam. That water goes through the dam, produces electricity, and falls back down to the lower reservoir lake again. So that's one other method that they have, but obviously knock-on effect with that is you need two massive lakes or reservoirs, one at the bottom of the big hill and one at the top. And there is a website you can go on, which I'll put in the links to in a moment, where you can actually see a sort of almost live view of how the UK is producing its electricity by different methods, what the demand is at the time, how much it's having to buy in from other countries. So certain times of the day, we actually purchase electricity and have it transported in from various other countries. Occasionally, we also export it when we're producing more than is needed. So I'll send the link and you can have a look at that as well. So there's not a huge amount about the national grid that you need to know. The bit about how transformers work, the only other thing that's worth adding there is transformers only work with an alternating current. So that's why we have to have this alternating current. So transformers only work if they have an alternating PD or an alternating current. So that's why we have an alternating current supply. Again, when we do the transformers topic in the magnetism section, that's when we'll look at those and how they work in more detail. So for now, you just need to know it's got to be AC because transformers only work with AC. They don't work with DC.